Hello, my name is Temirlan. I'll be presenting the novel kind of attack on machine learning, more specifically on neural networks. As we know, the usage of the neural networks, machine learning models, is quite being wider and wider, and the issues and concerns about their reliability and their security have risen. For example, there were well-known attacks like adversarial attacks, poisoning attacks, backdoor attacks, and now there's a new kind of attack. The attack that embeds malicious code, payload, or virus in weights of neural networks. So, as there were some theoretical researches, the research on countermeasures is absent. So our goal was to develop a framework to automatically embed malicious payload into weights. So it will allow researchers to continue their development on countermeasures and so on. So what's the methodology of this kind of attack? Suppose if we're a user and want to train a model or want to download ready-to-use model, if we want to train a model and we don't have computational power, we can use the service MLAS, machine learning as a service. We can use the service to train our model on the side vendor. But the side vendor can introduce malware into weights. So we can give the architecture to vendor, and he trains the model, and after that he embeds payload into weights and returns to us. And after the model works correctly, but if the model gets some input data with trigger, it automatically extracts the virus and executes it. What's neural network? We can consider it as a multi-layer, some mapping from input space to labels, and can be considered as architecture with neurons and weights. What does it mean to embed the payload into weights? As you know, in modern frameworks, as PyTorch, Flow, others, the most of the time, the weights of the neural networks are 32-bit float numbers. And float numbers can be seen as follows. The first bit represents the sign of the number. Next bit, the exponent of the number. And the last 23 bits is a fraction or multis. And the resulting number will be, as you can see, plus minus 1 point multis times 2 to the power of exponent. And what if we change the last several bits into arbitrary numbers? How it will result in the change? It has a small impact on the original number. The difference is not distinguishable. We can choose different numbers of bits and change it to the arbitrary numbers. We can take our malicious payload, divide it into the sections, and the section and the last bits change to the bits of these sections. So we decompose and embed to different weights. Okay, different weights. The next method is most significant byte method. It's pretty same, but instead of changing the last 7 bits, we change the last 24 bits and leave first byte unchanged. Why is that? Because previous method can embed less payload than, for example, this method. But as we embed more and more payload, the accuracy of the trained model drops. And in comparison with previous method, this method drops the accuracy of the trained model more severely. Next one is pretty same, but for example, if we take look at Alexa, pre-trained Alexa for image recognition, we can see that the most of the bytes starts with the specific byte 3C and BC. The difference is only the sign. So we can or starts or between them in the amplitude. So we can change exponent to that, and the last 24 bits we can change for the variables. The difference between this method and the previous one is that the previous one takes some time to decompose and to split and to merge the first byte with the arbitrary values. This in this method we look only on the sign of the value and just choose the first byte. So this method is faster, but the impact on the accuracy is more. Next one is pretty same. We change the half of the bytes. Yes. The next method is called resilience training. We choose neurons, the whole neuron, all of its parameters, and these parameters entirely are replaced with payload. But we choose the neurons randomly. So we need to store which neurons did we choose. So we need to store some vector or index permutation, as it is called. Okay. The next one is the value mapping. What the method is? If we have payload, we divide it into sections, and we perform an exhaustive search and try to find the parameters that look like our payload. This method is well suited for small neural networks compared to previous methods like SqueezeNet or MapIsland. The last method is sign mapping. Pretty same, but we represent our payload as a sequence of signs, and we find the parameters, that sequence of parameters that corresponds to our payload. So what is strong and weak points of this attack? Strong points is that it is effective at bypassing antiviruses and steganography methods, and can be combined with the other obfuscation methods or methods of self sorry, I forgot самоостановление. The weak points are that the attack is white box attack, that the attacker should know all the weights and should know all the architecture. The attack also drops accuracy of models significantly on the most of the times, and the attack assumes that the resulting model is immutable. So immutable because, for example, there is a point that we suppose that the user will use our model right off shelf without changing, without training it further. Training it may break the integrity of the virus. Virus can be changed. For example, this is the example of the most significant bug. Requires model and payload, and the payload should be embeddable. First, we store the number of replaceable bits, number of weights involved, and this metadata we embed into first parameters of the model. Then, parameter after parameter, we embed the rest of the payload. So, what's the drop of the accuracy of the models? If we consider the next models, first to squeeze out about small compressed ones, the next two are medium size, and the last four is a large models. And these models are pre-trained and we'll check the image network. So for the first method, plus significant bits. As you can see, for the large models, are extent and percent 1:1. The accuracy is either 0% or not significant. On the medium is but on the small ones, the method cannot embed payload. Payloads either from the smallest to the largest, from medium depth to largest. The next resilience student segmenting. As you can see, the drop of the accuracy of the resilience training is on the large models is there is no. On the small ones there is a significant drop of the accuracy. For the value mapping, the drop of the accuracy for the small one is way better. For the large and medium, percent mapping, there is no drop of the accuracy, but because we need a large number of parameters, the method cannot embed much of the payload. For most significant byte fast and half substitution, the results are quite the same as last significant. For the large, there is no drop of the accuracy to the medium there can be, but maybe not significant. For small models, there is drop in accuracy severe. So if we embed the payload, how to run it, how to execute it. First of all, I want to say about the trigger. When it will be executed. The trigger works as follows. We take the penultimate layer before the last softmax logits, and we compare logits to the stored ones. For example, if you want to model to work on specific image, the malware to be executed on specific image, we can take it logits, save it, and then compare it on the inference. If it is the same, then malware is executed. We can change. We can compare the signs. We can compare the ranks of the logits and other parameters. So this is how trigger works. But how how the execution works? There are three scenarios. First of all, if our model is accompanied by a third-party software, for example, if we provide software for Facebook recognition and it has the model with malware, then it's easy. We just activate function, the execution, we just get in the second one is the if model is downloaded or trained on yes, then we can change the forward function of the some layers to check the triggers and activate the function. And the last one is exploiting some vulnerabilities. CVs. For example, these two are exploiting the NumPy's bug. The last one and the second one is the exploiting the Google's graphical cards vulnerability. Okay, what are countermeasures? There are not a large number of countermeasures. First of all, is obvious using reliable sources. Second of all is retraining the model after training, compression, and other types of changing the network architecture. And the last one is monitoring the models. Let's say why we do this, because as I said at the first slides, the antivirus and steganography methods not work on this kind of attack because the payload is decomposed into parts. And the conclusion is that better not download from untrusted sources and untrusted providers. Is the main conclusion. Second conclusion is that we developed a framework that can help the scientists to further work on this kind of attack, on these countermeasures, and it's open source. You can test it on your own and that's all.
Thank you for your talk. And now it's time for questions. Yes, please, and please be a bit louder if possible because my But the speaker can also repeat the question.
Compression. How little compression can help us to find
It cannot help you to find, but it can help you to mitigate that the virus embedded in the neural network will be broken.
what's compression?
Uh,
Exchange bits if you use
Here, for example, using the not float numbers, but using the fixed floating numbers with a smaller space to embed the malware. Because as we saw, the methods work worse on the compressed models.
So do we have more questions? Есть еще вопросы? If we do not have more questions, let's thank the speaker. Thank you. And since the third speaker is on the way here, Dmitry, I would like to propose Ksenia Alexandrovna present her slides, which will. Давайте проверим. So